Good morning, everyone. Welcome to the Aerospike Summit 2020. This year, going virtual. It's very exciting to start with you all the first day out of the 3 for the summit. And I'm happy to pass the next 80 minutes with you talking about infrastructure for machine learning applications. We're going to split this into 2 parts. The first hour is going to be presentation and demo. And then we'll leave about 20 minutes for the Q&A. If you have more questions afterwards, just join our Slack. And let's go. My name is Natalie Pistunovich. On Twitter, you can find me at Natalie Pist. I am a lead developer advocate at Aerospike. I'm a Google developer expert for Go, the programming language. And so far, I was a software, hardware, and infrastructure engineer and engineering manager. I got to work at large companies like Intel, and I got to work at small startups with 20 people. Actually, that's how I got to hear of Aerospike. I was in the past on the side of the developer, and I love this product so much that I decided to join the company last year. Our plan for the day is to go over the steps of machine learning, discuss a little infrastructure for machine learning, see what is an example of a bare bones infrastructure for machine learning, go over a hands-on example and then do it in the demo, then recap, and then we'll have time for Q&A. So what is machine learning? According to Wikipedia, this is a scientific study of algorithms and statistical models that computer systems use to perform specific tasks without explicit instructions, relying only on patterns and inference. Machine learning is seen as a subset of artificial intelligence. What is artificial intelligence? In computer science, AI is the intelligence demonstrated by machines, as you could have guessed, in contrast to the intelligence that humans display, which is natural intelligence. This is a nice graph that shows the part of machine learning in AI, and you can see it's there alongside many other fields like natural language processing, text, speech, supervised and unsupervised learning, scheduling, planning, translations, and whatnot. So how to do machine learning? We can say that these are the steps. First of all, you define the problem. Are you doing face recognition? Are you looking at X-rays to detect any anomalies? Are you doing text recognition? Are you doing speech detection? Are you doing translation? Are you looking for fraud in online purchases? And how do you define success with your problem? Is it a fast response time of a few hundreds of milliseconds? Is it an accurate answer with a high accuracy of 99.9%? Once you have that defined, you gather data and you make sure it's relevant to the problem. For example, if you're doing text recognition in English, you probably don't want to have Vietnamese characters. And then you take your data and you prepare it. You clean that, you pre-process, you make sure all the images are centered, you randomize it so that the computer will not learn that after 4, 5, 6 would come 7. And you split your data set into training data and to test data, roughly 75-25%. Then you choose your model. This depends on many parameters. For example, what is the problem as we have defined it, but it's also what is the input type and what is a categories number. Categories is basically the number of potential outputs. So if you're doing text recognition for Latin languages, anywhere between 20 and 30 is your categories number. If you're doing digit recognition, you have 10 categories. If you're doing face recognition, you have thousands or millions, of categories. And if you're doing hot dog, not hot dog, you have 2. You chose a model, and then you do training. Step 1 is assign random values to the weights on the graph. Then you make a prediction, you evaluate the results using the 75% data from the training data, which is also the one you trained with. And then based on the results, you adjust the values. Many times this is a process done by the computer. And if this is sounding familiar to you, this entire flow, this is because the same steps are taken when you make differential equations and you solve them. Once you're done training, you're evaluating the model using the remaining 25% of your test data. And here, many times, you'll find yourself falling back to stages 4 or 5, where you either need to retrain the model or just choose a different one. But if all goes well, you move in to step 7, and you tune the hyperparameters. And this is fine-tuning, and this is mostly done manually. Once you're all set, you're ready to do predictions. One of the great tools for this is Tensorflow. It's an open source software used for machine intelligence and all kinds of learning applications like neural networks. And it has a tensor, which is the mathematical representation of your data. Its generalization of vectors and matrices can be of high dimensions. And you define that with 2 properties, the data type. So is it string, is it integer, is it something else? And the shape of it, which is number of dimensions and number of values per dimension. In this image, we see a physical representation or a physics tensor. The mathematical one that we're using here is slightly less complex in the representation of it. And our tensors flow through the graph. The graph is the model, and it's made of a set of nodes. Each node represents an operation. And at any step of the flow of our tensors through this nodes, you can inspect and see the intermediate value, which is the output of all the operations that have been performed on the tensor so far. So basically, our data in the form of tensor is flowing through the graph, which is represented by a set of nodes, and it is the model that we chose. Let's talk about infrastructure. This is a great article written back in 2015, still very much relevant, about hidden technical debt in machine learning systems. And if I need to summarize it, I can say that hacking a machine learning infrastructure around the model would lead to an increasingly complex technical debt. And you should plan your infrastructure carefully, especially if you're going to production. This is available on the internet openly to anyone. Write down the name, and I really recommend to take a read later. There is a lot more to machine learning than just implementing the algorithm. Actually, the code of the algorithm accounts for about 5% of the overall code of the system. The rest of the code lies in processing the data, transferring it through the system, doing serving, doing monitoring, and making sure that everything functions. Let's look at one example of what a bare bones infrastructure of a machine learning implementation looks like. And I want to say that this is my personal opinion, and you'll find multiple different examples, and that's fine, and really depends a lot on the use case. So we start with data. And the data comes in lots of shapes and formats. Parquet files, JSONs, CSVs. It can be also images, it can be also sound files. And the very first thing you need to do on them is process the data. For example, if you're not PCI compliant, but you are receiving information that includes credit card information, you want to hash that before that enters your system. And then you store the data. You can store it in a data lake, and that's a name for a platform where all the information stored in the raw shape in an unhierarchical manner. And it's huge and it's a lot and it's a lake, just like the name represents. And you have the database where you have the data stored in a structured manner and the clear accessing APIs, and everybody can easily pull out information from there. And your next step is another iteration on the data. Here, for example, things you do is making sure that each team that has access to the data will get the information that should be not visible to them masked. And you can also consider creating a subset of the data, anonymizing it as much as needed, and publishing it as an open source. Once you have the data ready, you do training to the model. Here it's important to mention versioning. You want to version your data and you want to version your model. You want to do this for multiple reasons. One, for example, is that if you have to remove some part of the information, like happened with the GDPR rules a few years ago, you should be able to do this in a very easy way so that the data is not existing in your system and a model that was trained on this data is no longer in use. From our steps of how to do machine learning, this lands us here. And you can roughly separate training to two types. You can do the static model and you can have a dynamic model, online versus offline. Static model basically trained locally, and then all the outputs are uploaded. So it's easy to build, it's easy to test, all the predictions are done ahead. And the cons is that it can only predict things we know and trained about. And if you do choose to update, you have to do an update on the entire thing, and this will take a few hours or a few days. Dynamic model is being trained as the input is coming in. For example, you made a prediction that some transaction is not a fraud, but then a chargeback came into your system and you have to update that this was a fraud. You do this live. The good thing, of course, is that it's adapted to changes and it's more likely to make better predictions, especially as the time goes since your last update of the model. But it's compute intensive, it can take longer time, so you have to put some limitations on it and you have to monitor both the outputs and the performance. All right, so we have our model, we trained it, then we feed it to a serving platform, function as a service, or as it's called these days, serverless, and that makes the prediction. This puts us in this stage, and you can also split this into roughly two types, online and offline. The online inference can make better predictions as new items come in, and it's great for a long tail. Think about the example of a flower shop. Based on how many purchases you have, this will make recommendations. How many flowers should you order for the future? And online inference will know that as the weekend comes, it will recommend you to buy slightly more flowers, but as the days of the weekend ends and the beginning of the week comes, you want to order slightly less. But then it notices this behavior around February 10th, that more flowers begin to be bought even though it's the middle of the week, and even a higher increase on the 11th and on the 12th, and it can make the recommendation to buy a lot more flowers. And then you find yourself on Valentine's Day selling all the flowers and not missing out on the most profitable day of the year for flower shops. Of course, the cons are the computation, the latency, and the monitoring needs. An offline inference has a predictable low cost. It's very likely to use batch quota, and you can even verify all the predictions before going live because that's basically one big lookup table. The biggest con is that it can only predict based on the information that we already know. The last and the most important step is the monitoring. We said we want to monitor the output, we want to monitor the results, we want to monitor the performance, we want to monitor maybe a lot more requests coming in, and we want to put more resources to the system. And this is what I see as an example of the bare bones architecture for machine learning applications. But this is not the reality out there, and there are other examples of tools that were not included in this bare bones applications. And just to give you an example, this is a snapshot of the AI market in 2019. And if we zoom in a little bit, there are so many more tools and fields that we didn't include, like AI ops and like storage and like hardware and data transformation and search and visualization and collaboration, and of course security. So there's a lot more to put on top of that. And as I said in the beginning, that's my opinion of what is the bare bones infrastructure. And there is a lot more to add depending on the use case. Now let's look at a concrete example, the one that we'll be implementing also in this workshop. And as you can guess, this is very similar to the bare bones architecture we saw. We want to see which of the credit card transactions that enter the system are fraudulent. So we have a website where we sell things, or maybe we aggregate online shop for multiple sellers. And from each transaction, we get information like the user ID, the seller ID, the item ID, the credit card hash, and we also get additional information like what is the amount of the purchase, what is the timestamp. And this goes into Aerospike. And then we're creating a feature vector. A feature vector is a mathematical representation of all kinds of features. So instead of asking, how long has this user been registered, we give this a numerical value. And we ask many other questions that will help us to make a better predictions. For example, how long has the seller been registered? How many of the seller's transactions were reported as fraud? How many items does a person buy on average from the seller? What is the average purchase amount for each seller or for each user? How many fraud reports each user has, and so on. And we create this vector that has this numerical values. And this is the output from Aerospike. So what it does, basically, you can say it's an enrichment. We have an input of several criteria, and we have the output of several of tens or even hundreds of criteria or features, if you will. And this is being fed into the machine learning model. And of course, it's better to have a lot more data points than just a few, because this will help our model make a better prediction. And then the output of the model is a value, which is the percent that it expects it to be fraudulent. And depending on the threshold, the decision whether it's a fraud or not fraudulent transaction is being made. And it's time for a demo. So the workshop, or the hands-on part, will be The demo part will be the hands-on part, and the way we will do this is we'll first put the building blocks, so the database, for example, and then we'll write the code that connects everything. The building block, the main building block here, is where the enrichment is happening, and we'll be using Aerospike for that. The data that you're storing for finding frauds in online transactions is around user, seller, item, and all the surrounding information, for example, purchase history, fraud history that was reported, properties of each one of the entities. For example, for the user would be location, average amount of purchase. For a seller is average number of items per purchase, or now average amount of purchase, and so on. And a lot of those structures is one-to-many, and they can be tracked by a list or a map with an object ID, and then you just do a batch read on that list. Several large clients are using Aerospike for fraud detection, and they are making a massive use of batch read to fetch related objects, not via SQL join. In the next workshop, document-oriented data modeling, you can see an example of a similar structure used for a different purpose. When you look at the information that you have to make a prediction whether the transaction is fraudulent or not, you're looking at many data points. Let's focus on 3 of them. Location is the first one. So you're having these clusters of purchase by geo, and you determine hubs with machine learning. Let's say I usually shop online in the radius where I live. It can be that I'm making some kind of an online transaction when I'm traveling, and then it's likely that there'll be several of those. So maybe the first one will be suspicious, but the following ones would be more reasonable to be there. But if I've just made a transaction in my regular place, and shortly after there's another transaction, especially if it's a large one, from another place in the globe, that is probably suspicious. The second data point is purchase habits. Aerospike is great for historic data as well as transaction data. You can model a user through a credit card and then normalize it into an embedded list of maps. You can look up the index for the credit card to the user, and again, no need to do join. And the third data point is actually tracking the items. How often am I buying swimming gear is one example. Let's say I need new goggles every few months, and it can be that I'm often buying this from the same seller, and then it's the same combination of an item ID and seller ID, and then a new seller comes in and offers a better product or the same product for a better price. So I'll be buying from a different seller with a different seller ID. It probably has a different item ID, but it also is probably having the same category as the previous item. So it's sports gear, maybe swimming gear, maybe even subcategory of goggles. So this similarity in the set of features is likely to indicate that it's most likely not a fraud. In our demo, we'll be deploying Aerospike via Docker. Why Docker? Mostly because it's so straightforward. You're downloading the image and you just start running. No need for any particular installation. You're always easily updating. All the version releases are always in sync with the server releases. And it's easy to inspect the resources that you're consuming. There is a great talk about starting with Aerospike on day 3. I recommend you all to listen to that as well. So there's many ways to start other than Docker, and that's why the part of the code connection will be actually using Go, and I'll be doing this on my local machine. To my favorite question, why Go? I have a long answer that I'll try to make short. Go is fast. Go has a great garbage collection and it's type safe, so it's also strongly typed, so it's very hard to make mistakes even if you have some unexpected inputs. It is open source and it's backed by tech giants, so you cannot say this is a hipster language, but it's actually there to stay, and by now it gained credibility. Many modern tools for DevOps and infrastructure are using or are written in Go. For example, Prometheus, for example, Helm, for example, Kubernetes. Many open source tools are written in Many modern DevOps and infrastructure tools are written in Go, including Prometheus, Helm, Kubernetes, Grafana, and many others. All the tools that I mentioned, we have connectors for, and as Aerospike recently joined the CNCF, the Cloud Native Computing Foundation, we have a client in Go for a while. Many modern tools for DevOps and infrastructure are written in Go. For example, Prometheus, Helm, Kubernetes, Grafana, and many others. With all those tools that I mentioned, we have integrations. They're all written in Go. And actually, many of the tools that are supported by CNCF, the Cloud Native Computing Foundation, are written in Go. Aerospike recently became part of CNCF. We're big supporters of open source. That's why we created connectors to all those tools, and we keep working on that. Why so many tools for DevOps and infrastructure were written in Go or rewritten in Go? Systems become more complex, and the code that you write to connect them and to make sure that the engine behind it is running requires real code, not just some glue scripts. You want to revision it, you want to test it, and you want it to be easily readable and accessible by everyone. Go is a great language for this purpose. It also has cross-compilation as easy as using a flag. So you're just running the command, you're writing the flag of which architecture and which operating system you're writing for, and you're good. And there's one binary for everything. It includes the external libraries, it includes the dependencies, and it removes the thought of the being dependent on latest versions or releases off your head. So as a DevOps person, you're just writing the code, and it's good to be shipped anywhere as one binary. From telling about myself earlier that I'm a Google developer expert for Go, you may see the bias that I have. So I'll stop telling about how great Go is, and we're gonna move back to our infrastructure. So let's write some code. Right now, I have an empty folder. I have Go installed, and I have Docker installed. And the first thing that I'm going to do is pull a Docker image off the Aerospike server. Aerospike server. Downloaded, so let's start it. Server. So the command that I'm going to be using is docker run. PID for the interactive terminal. The name of the container is Aerospike, and I'm going to be mapping the ports from 3000 to 3003, as is from my machine to Docker, and the image that is running is the Aerospike server. Great. Next step is pulling the Docker image for the tools. Docker pull Aerospike tools. In the tools image, you can find all kinds of tools that are useful. The two that we will be using is the AQL that will allow us to inspect actually what's inside our database. And we'll also be using the AS loader, which will allow us to just migrate a CSV. To save time, I've already pre-downloaded this, so it's just a quick checkup that nothing new since the last pull, and indeed nothing new. And so let's run AQL and see what do we have. So this command is docker run -it, interactive terminal. The name of the image that I'm running is Aerospike tools. And then inside Aerospike tools, I am calling AQL. And as a local host, I am just inspecting my IP address from the network settings, and this is what I'm sending. All right, and I am inside the AQL shell. So let's see, what do I have there? Show namespaces. Empty. I have the default namespace. Let's see if I have any sets. Nope. Empty. Let's insert one entry. Insert into test, which is the name of the namespace, dot credit card, which is the name of the set that I'm going to be creating, and primary key into the bin ID, and the values that I'm transferring are the key and the value. Great. Now let's see, what do I have? There you go. I have a new set named credit card. It has one object inside. I exited AQL, and now I'm going to go back in just to make sure that I have what I expect to see, which is the value that I've just set there. So typing show sets, I still have the same thing. And let's see, select everything from test.credit card. There you go. I have a bin named ID where I've populated the value 0. Super. So, all right, now let's download the dataset, and we'll be getting it from Kaggle. We will have the credit card fraud detection dataset. That is a CSV with roughly 300,000 anonymized transactions of credit card by European users. Let's hit download. And while it downloads, let's inspect the content of it. All right. So, the first column is time, and it's an integer that represents the number of seconds between this transaction and the first transaction in the data set. Then we have 28 columns of floats, and then we have a column for amount, which is the transaction amount. It's also a float. And we have the classification, which is 1 for fraud and 0 otherwise. Now, what are those PCAs, you're asking? It stands for Principal Component Analysis, and it's done by calculating the data covariance matrix from this data that we have, and then performing eigenvalue decomposition on it. This is the mostly used tool for making predictions, predictive data models. And you can think of it as taking the real transactions data from credit card number or hash to number of purchases, number of items, descriptions of items, history, like how many fraudulent transactions this user has, and so on, and calculating that into a vector representation with a numeric value. This is how the data looks like. First column is time, then we have the expected 28 columns of V, and then we have the amount and the classification. So integer, 28 floats, 29 float, and a string, which is the prediction. Let's look at our tool for loading data, Aerospike, and see what do we need to do. Scrolling all the way down, we see that basically you run this command and you need to give a configuration file and the data file. Looking at the examples, here is how a config file should look. So version 2.0, the delimiter is defined, the number of columns, and whether there's a header. And in the mapping, we have, first of all, the name of the column for the key and the type. And then we have the set name, where it goes to, so to which set in our database we're importing this, and the type. And then this is the bin list, so that's an example of some of the values that you can have. And in addition to the default ones that are listed here, you can also have geo and more sophisticated types. So let's write a config file, and let's make sure that we add a key and a set columns to our data set so that it will be in the right format for importing. So we want 2 more columns in the header, or 2 more names for columns in the header, and 2 more columns in the beginning of each entry. I'm going to write a quick bash script to do this for us. So now we have this config file. As we said, this is a DSV delimited by a comma, 33 columns, because we have the set, the ID, the time, then we have 28 columns of values, and then we have amount, and then we have the prediction. And the mappings are, the key is named ID and its type string. The column name is set name, it's also type string. And this is telling us to which set we're mapping the information. And then we have time of type integer, 28 floats for the PCAs. And then we have the amount, which is also a float, and the classification, which is a string. And the new version looks like this. There is an ID, there is a set name, and the rest of the column names that we saw. And each transaction got a unique ID as well as a set name. Now, let's import this. For importing, I'll be using the Aerospike tool from the image that we already have of Aerospike tools. And I'm using Aerospike. All right, so let's look at the values that we have. Docker run, IT, we know that one, that's interactive terminal. And then we say, from where I am, mount all the content into a folder named data inside the Docker container, and start the image Aerospike tools. Call the specific tool Aerospike, give the localhost the same one, the IP address, port 3000, which we've already mapped. And for the configuration file, from the locally mounted file folder data, take the config.json, and the file that you will be migrating or loading is the credit card CSV. So it shows us the progress, and it already imported 10,000. I want to remind that the entire data set is around 300,000 transactions, and to be precise, 284,807. And it's complete. Successfully written the 284 807 transactions. All right, let's go to AQL to inspect what do we have. AQL. We are in the AQL shell. So please note that it took under 20 seconds to import 300,000 transactions, where each entry has 33 columns and most of them are floating points. For the demo that you can try at home when you're trying Aerospike, you probably have all sorts of CSV files you can try, like the example we use with Kaggle. And I guess that a lot of the questions that are going to come in the Q&A part will be about importing or migrating or loading data that you already have. So let me just give a quick heads up and say that there is tooling. The workshop that is coming right after this one is on data modeling. And if you have interesting use cases that are not straightforward CSV, we have an awesome team of solution architects to do the migration together with you. Okay, so we said that what we will do is put the building blocks and then put the code around it. So we built our database with all the feature vector that will be coming out of it. So let's do the code part, and we'll start with a transaction that is coming in from the web with all the features that we mentioned. So let's start by initiating connection to GitHub. I just opened a new repo, copy the code, and I'm going to paste it here. Okay, connection set up. Go mod init. So, go mod init.com/Pistunovich/infra/ml/s. Okay, so now we have the modules set up, and we have a README and we have a Go mod file, which will help us handle our dependencies whenever we're going to import the library. And let's kick things off with a main.go file. So first of all, store it as main.go. Then we add package main. Yeah. And the first thing you do in a Go profile, Go software is write go.mainfunc and save. And well, we have our very basic main.go file, which does nothing. Let's add a struct with the transaction as we define it coming from the web. And the syntax for that is type web transaction and it's a struct with the following fields. Timestamp is a string. Amount is float 64. Then we have user ID string, we have seller ID string, and we have item ID string, and we have credit card num hash, also a string. And one more important thing is something to help us handle errors. Go is very known for not allowing you to put something like a point to do debugging around, but it actually returns errors and you're expected to handle them. This is a great example of how not to handle errors, and because what you do is just panic, and instead of understanding what is the content of the error, which is usually informative in Go, you just say, oh no, and quit. So we have what we need. So if the error of the input to the function is not new, just panic, which means kill the program. And then what we'll do in our main is we'll define an instance of the struct that we defined of web transaction. And this will basically imitate what we see coming in from the web. So let's populate it with field. Timestamp is a string, so let's say it's 2. Then we have amount, let's say that is 23. The next fields are user ID. Let's say this is this one. Then we have item ID to be something else. Seller ID, another field, and a credit card non-hash to be perfect. We have ourselves a struct, and right now it's complaining that we declared a variable but not used it. That's one of the nice things about Go. If you have unnecessary variables, it will not allow you to continue. But we're going to make use of it because we're opening now a connection to the database, and we're utilizing the fact that we have a client running, new client, and it will be in 127.0.0.0. It's fine because we defined it locally. And we say panic if the above is an error. Now at the moment, this will say that there's a problem because it doesn't know what is arrow. And we need to tell them what it is that we want to import because we're not using a standard library. I'll copy it from here and going back, import this as arrow. Perfect. And now I save and everything works. Now the next error is that we have client which is declared but not used, and still our incoming transaction is declared but not used, but we have ourselves a connection to the database. So what we're going to do with this connection is try to write this incoming transaction to the database. So we're going to define a key. Error, new key. And the parameters that it takes is the namespace, the set name, credit card, and the value that we're going to write that into, which will be incoming transaction from the field seller ID. And if there is an error, please panic. On error or error. Next issue would be that we are not using the key. Even though it's declared, we're still not using the client. So the last thing that we need before we make this right is also define an incoming bin map. Incoming bin map is arrow.bin map. bin map represents the input that we're actually going to store into the database. And we will reuse some of the fields from the incoming transaction, but we cannot reuse all of them because we only have 1, 2, 3, 4, 5, 6, but each entry has 33 columns. So into ID, we will write incoming transaction dot seller ID. Into set name, we will write credit card because that's the set name we want to make this connection to. And into amount, we want to set seller incoming dot amounts. Perfect. And then it's closed. And now comes the part that connects all of them and will stop this error, or the 3 underlined errors. Error is client dot put. The first value is nil because we don't have any particular policy. Then we add key. Then we add our incoming bin map. And this all goes into error. And of course, we ask to panic in case there is an error. Perfect. All right, let's save this. Go run main.go. Let's see what's the output here. So it all looks good. Let's just change this to the correct one. And run main.go. And this seemed to have succeeded. So the last thing we'll do is get the value back. For that, we will set a new key. This one is going to be called GetKey. And we are using the Aero client and the function key that receives the namespace test, the credit card set, and the key is the incoming transaction field, the seller name. Please panic if there is an error. Then we're going to create a new record and use the client to do get. We're not requiring any particular policy. The key we want to use is the one we just created. And of course, we want to panic if there's anything wrong. And hopefully we got everything right. All we have to do is print. So we're going to print the value record dot bins. Saved, no errors. So let's run this. And we got back a map. Now let's compare it. The amount we received is 23. The ID is 222, yeah. And the set name is credit card, exactly as we defined. So there's a great talk about the different clients, including the Go client, by the person who wrote that. This will be on day 3. It will cover the architecture, and I can definitely recommend attending that. And some notes to wrap up what we did. If we had real data, so not just a floating point representation of the vectors, but or the PCA, but actual real information about transactions, we could have written a lot of functions to create different input fields that would be the core of this enrichment that we talked about that is happening in Aerospike, because it's basically given seller ID, get out all the historic data, process it, including the newly incoming transaction. And then this is what will be fed to the model. So a lot of data points based on the historic data, and you're saving that. But as we have in this data set just a vector of the feature in the mathematical representation, this is what we are able to do. And some things that we could have done if we had this information is, for example, average monthly purchase amount or number per user, average transactions number per user, per seller a month, percent of the fraud transactions that a seller has, and so on. For model training, Go is not a suitable language. Python is, of course, the default for anything machine learning, but serving the model, so making the predictions, is definitely possible with Go. You can use Tensorflow, you can use PyTorch, or you can use any other tool or technology, anything in-house that you have. The serving of the model, if you want to just try it on your machine, a tool like OpenFast is a free and easygoing solution. It's also part of the CNCF. And there's many other solutions. You can use it as a microservice in your production, just part of the monolith and whatnot. It's also very important to mention monitoring. Please monitor the results. Please monitor the performance of the system. Please monitor how many connections you have, how many transactions go, if there's any timeouts, if there's any idle connections, and utilize all the new connectors and the features that Aerospike has connecting to tools like Grafana and Prometheus. So this is the infrastructure that we've built. And what we went over is what is AI, what is ML, and how to ML. We went over the differences between online and offline training of a model and inference using a model. We covered what is one example of a bare bones architecture and what are the components of it. And then we saw a concrete example. Maybe some of the customers in the crowd can recognize it. And then we had a demo and actually built parts of that on our own. The code of a machine learning algorithm is about 5% or less of the overall system. The input data is a big and it's tricky part, and it's usually slowing you down in the calculation because you want to give as many data points as you can, but processing them every time takes a lot of time. So you need a solution like Aerospike to just store all the historical data and do the batch read every time you have lots of transactions going on. A good bare bones flow would be processing the data, storing it, training the model based on that, serving the predictions, and of course monitoring the entire thing. Thank you very much. Please stay in touch. I'm on Twitter, Aerospike is on Twitter, and this is the hashtag of the conference. You can write me an email if you have questions or if you want to try something. And please join our Slack. The invite link is really straightforward. It opens a Google form where you just fill out your email and we're sending you an invite to the Slack channel in the Aerospike workspace. And you can stay in touch with all the attendees and all the presenters. And I'll be there as well. Thank you very much again. And let's please move to the Q&A part.